Hello, so these are the deltaH equations. There's two you need to know. First of all, we need to know heat equals that badass rapper MC delta T, you'll get me blood. And we also need to know deltaH, enthalpy change, equals plus or minus heat over N. Okay? There is a third one you need to know, but you should already know it by now, which is N equals mass over mR. When we're using these equations, this first one is talking about the surroundings. I've said this a billion times to people and people still get it the wrong way around. Please try and remember, otherwise I'll end up crying in a corner in the fetal position or something. So heat of the surroundings equals the mass of the surroundings, that's M, times by the specific heat capacity of the surroundings, that's C, times by the temperature change of the surroundings, which is delta T. So heat equals mass times specific heat capacity times the change in temperature of the surroundings. Okay? So if it says you have 7 grams of chemicals and 100 grams of water which gets heated up, the mass is not 7, because that's not the surroundings, is it? That's the chemicals. It's going to be whatever we said for water. Also, a little tip, 1 centimetre of water weighs 1 gram. So if you have 50 centimetres of water as your surroundings, your mass is 50 grams. Specific heat capacity will always be told to you, and that's basically how much energy it takes to heat 1 gram of your stuff up by 1 degree C. In some books it says 1 Kelvin, but in your specification it's 1 degree C. And that's always told to you, and if it's water it's 4.18, so I'll just make a note of that up here. And delta T, change in temperature, that's just the difference between your start and final temperature. Don't get it the wrong way around. If you started at 20 degrees and ended at 40 degrees, that's a change of positive 20, because it's gone up by 20. If you started at 20 degrees and ended at 10 degrees, that's a change of minus 10, because you've gone down by 10. So don't forget to get the sign the right way around. Okay? So this is your surroundings. This equation here, in fact, I'm going to write it down. In fact, I'm going to write it down twice. And just to make sure, I'm going to write it down again, but in a different coloured pen. And I'm going to highlight all 3 of them. And put little stars coming off them as well. So if anyone forgets that, they're an idiot. We've also got this equation here, which is delta H, your enthalpy change, what we're trying to figure out, equals plus minus heat, and I'll explain that in a second, divided by N. And N is the number of moles of your chemical. Because all this equation is talking about your chemical. That's the surroundings, this is the chemical. Or the chemicals. In order to figure out moles, we use moles equals mass over mR, but you should already all know that. Okay? Again, mass of chemicals, mR of chemicals, because it's the moles of the chemicals. Okay? So basically, first of all, we'll take our mass and our specific heat capacity and our temperature, multiply it together to get the heat. So let's say this heat comes out at 50 joules, and the units of heat is joules. So I've got 50. So that means my surroundings have gained 50 joules. Now if they've gained 50 joules, that means my chemicals must have lost exactly 50 joules. Because the amount the surroundings increases by is always equal and opposite to what your chemicals have lost. And vice versa. If your surroundings lost 50 joules, that means your chemicals must have gained 50 joules. So in my first equation, I calculate the heat lost or gained by my surroundings. If I flip the sign of that, I then have the heat lost or gained by my chemicals. So the only reason we do this is to find out the heat of our chemicals, and we do that by flipping the sign. I then divide that by the number of moles of my chemicals, and that will give me my enthalpy change in joules per mole. If I want to get that in kilojoules per mole, which they always ask for it in, I need to then divide by 1,000. So I'll go through an example calculation. Lucifer heated 100 centimeters cubed of water from, that's nice, from 16 degrees C to 23 degrees C. This burnt 10 grams of, I don't know, methane, CH4, okay? So we've got some CH4, burned 10 grams of it, and we heated up 100 centimetres of water from 16 to 23. And unless you can't tell, I am just making these numbers up, so this isn't going to be anything like the actual number, okay? So what we need to do, we start with heat. Heat equals MC delta T. My mass is the mass of my surroundings, hopefully we can remember that, which is 100 centimetres, 1 centimetre is 1 gram, so that's 100 grams. My specific heat capacity, 4.18, will always be told to you. And my temperature change from 16 to 23, that's positive 7 degrees. So I'll put it in my trusty assistant, Mr. Calculator. 100 times 4.18 times 7 equals 2,926. And that's a positive number. So I'm just going to take that and I'm going to write it back at the top because I need space on my board. So I know heat of surroundings equals positive 2,926. I know my heat. The next thing I need to do is calculate my moles. So moles equals mass over MR. So the mass I burn is 10 grams and the MR of this will be 16. I used a simple one just to save time. In your exam it will probably be a lot more complicated than this. So if it is very complicated, just double check it. A place where a lot of people make mistakes is they don't add up the MR properly. I know it's always really tight in exams, but it is worth just checking your MR just once again, just to make sure. Otherwise you'll lose 2 or 3 marks for this. Okay, so 10 divided by 16, 10 divided by 16 equals 0.625. And remember, if that was a really, really long answer after the decimal point, don't round it till the very, very end of your answer, okay? And when you do round, you round to as many significant figures as the least accurate number in the question, okay? So, I've got my moles equals 0.65, I'm just going to write this up here too, because I need the space. That's the data I've got. I can then use my third equation. The change in enthalpy equals, flip the sign of the heat divided by moles, which is going to equal minus 2,926. Remember, you flip the sign because it's not the surroundings we want, it's the chemicals. And if the surroundings gain that much, the chemicals must have lost that much. Divide that by the number of moles, which is 0.625. Bang that in the calculator. 2,926 divided by 0.625, and that will give me 4,681.6. Don't forget the minus sign. Remember, this answer is in joules per mole. They will almost certainly ask you to give your answer in kilojoules per mole, and if you forget to do that, you're going to lose a mark because you've not answered what the question's asking. And it's a really silly way to lose a mark. So to get from joules to kilojoules, I divide by 1,000, so my final answer will be I haven't done this, but usually they go to 3 significant figures. So let's say it was 3 significant figures, 4.68 kilojoules per mole. If it had gone to 2 significant figures, it would be 4.7. Yeah? If it had gone to 4, it would be 4.682. Okay, so you just round up or down, just simple maths. And that is how we calculate the delta H for a reaction based on experimental values.